right, so good afternoon, everyone. Please, actually, if you still have one seat next to you, do raise your hand so that a couple of people can still sit down. It's a session that's going to be on chaos engineering. I'm part of the evangelist team myself. And before we get started, I just want to have a little understanding of the audience. How many of you practice chaos engineering today in your company? OK, I'm not talking just chaos. I'm really talking about chaos engineering, because I'm pretty sure everyone has chaos. I saw 2, 3. OK, cool. So this session is really for you. So I'm part of the evangelist team, obviously. And I've been working on large-scale systems for about 10, 15 years, depending on how big a system was and when you start. But I always loved breaking things. And I'm pretty much sure that yourself, you had Lego bricks or things like this when you were a kid, and you love to break things. And I think kids love to break things because that's the way we can learn about stuff. And chaos engineering is pretty much around the idea that breaking is actually a way of learning. And hopefully, I can give you these kind of ideas in about 1 hour. So why do we talk about chaos engineering? This is actually an interesting picture. This is the constellation of microservices of Amazon.com in 2008. OK? Things have changed quite much dramatically since then. Actually, it's increasing. This is Twitter, and this is Netflix. So pretty much the idea of having 1 or 2 services doesn't apply anymore. And if you have maybe 5, 10 services working together, the idea of the system working all the time is kind of normal. We call that full working system, right? We have 10 services. The normal operation mode is everything should work. But when you have as many services as that, the normal mode of operation doesn't apply anymore. Because at any given moment in time, there's going to be some failures happening in the system, right? So failure is actually something that happens all the time. And since you want to operate in a mode where failure always happens, we call that partial failure mode. So that means it's a mode where failure is tolerated, right? We embrace failure. We say it's not because we have failure in the system that we should not work. We just go into a partial failure mode or degraded mode. And this actually is a real video. It's a base jumper in Norway that wanted to make a good entrance into, I think, the world of gymnastics, so to say. And why I like this is it didn't die, right? Actually, it didn't die. I wouldn't put a video of someone dying on the stage. But he survived because he had a parachute. OK? And this is exactly what we want, right? We are operating in failure mode, but then we have a degraded state. And he survives, and then eventually managed to do one successfully. So this is exactly what is the idea of partial failure mode and degradation. Now, when we talk about this, we often talk about the word resiliency, right? And this is exactly what resiliency is. Resiliency is accepting that there's going to be some failures. Now, when you expect that there are failures, often people think that there are failures on the infrastructures. This is kind of the first things that people have in mind, is like a network connection that is breaking or electricity that is breaking. But actually, failures come from the network infrastructures, or the infrastructures go up to the network and data, to the application, and even of people. And we're going to talk about some of those patterns a bit further in the presentation. But when you operate in those systems like this, the normal testing framework, like unit testing or integration testing, pretty much don't work anymore. You have 1,000 services, right? I'm pretty sure no one can build a test to really test these kind of things. So what you need to do is try something else. And what we do is we move testing as close to the production system, right? So because that's the only place where we could really test the real system is on the production. We have thousands of microservices. We can't have a staging with 1,000 different microservices. So we try to bring testing close to the production environment so that what we do is kind of realistic. And we started to do this at Amazon in the mid-2000s. In the mid-2000s, Amazon.com was growing a lot. we started to have a lot of data centers worldwide, and we brought one guy called Jesse Robbins. Right? We hired a guy called Jesse Robbins, and Jesse Robbins was quite particular. He actually was a firefighter during his spare time. And do you know what's very uncommon with firefighters compared to the rest of professions? Want to guess? They practice fighting fire 80% of their time. Right? And do you know why they do that? So that the 20% of the time where they go and fight a real fire, they have intuition. They have intuition on how to fight fire. If they think about the fire, they're dead. So they have to develop an intuition, and you develop this intuition through testing and through practicing. Right? So Jesse Robbins came at Amazon and brought a system called GameDays. And those GameDays were the early days where we were practicing chaos engineering. It's basically, we would, or Jesse Robbins would just randomly start unplugging servers or shut down the electricity and he would, or anything. He would just really randomly go into an engineering team and say, okay, let's try if the system is going to go down. They went even at closing the whole data center. The first time he did that, it actually didn't go well, right? So there was a lot of issues, but through the different times they practiced closing data centers and breaking things, they built a lot of resiliency, right? They started to understand what was happening, and eventually the system became pretty resilient. But chaos engineering actually really became popular through a company called Netflix. Right? Netflix, I'm pretty sure you know Netflix. I don't have to reintroduce Netflix. But Netflix in 2012 experienced quite a big outage that was responsibility from AWS. It was not Netflix's fault. After that, they went into architecting a very big multi-region system, which I talked of yesterday. But this architecture, this global architecture was something they couldn't test with normal testing tools. So they developed tools called the monkeys. And the whole monkeys, they have different of them. They are called the Simian Army. And those monkeys are software systems that basically Netflix runs randomly inside their AWS account to break things. The first monkey that was launched is this little monkey here called Chaos Monkey. And it would randomly go and switch off instances, EC2 instances, in an account and say, oh, if the system is supposed to be resilient, I should be able to switch off anything, right? How many of you how many of you will say, I think the system is resilient, but please don't try, right? It's often like this. We have system, and we hope the system is resilient, but let's not really try because in case, right? Do you practice killing your database regularly? How many of you do that? Yeah, it's a very few, right? What if one day it will go down? Because actually, it will go down one day, right? Failures always happen. There's no room, there's no world where failure doesn't exist, okay? So Netflix embraced the idea of failure and created a tool to test pretty much everything. Testing security groups, testing networks, testing even the resiliency across region failures. So the big monkey, the gorilla here, once a month go randomly and kill a region inside the Netflix AWS account. And then they can practice moving traffic from one region to another. And they do this while you watch movies, okay? So they've become so good that users pretty much don't realize when this happens. So the Simian Army is pretty cool, right? And what is it really in general? Basically, chaos engineering is really injecting failure. So the same way as we build resilience in our body against sickness, we inject vaccines for us, our body, to create antibodies. In a software system, we do the same. We inject failures. And we inject failures at a lot of different levels in the system, on the application level, on the infrastructure level. So some cool attacks on the infrastructure level is say, OK, let's unplug the network, right? Do we have a resilient connection? Let's add latency. You know, latency is a terrible sin, right? It can destroy a system. On an application, you say, OK, let's remove the cache, or let's kill a database, or let's simply remove a load balancer and see what happens. But that's not only that. One of my favorite attacks is actually a poll attack. It's a human attack. How many of you have in your company the one person that does everything? He's like a magician. If he's not coming at work, nothing is pretty much working. No one knows how he does things. He's just, oh, yeah, I'll fix it. I'll fix it. Yeah, I'll go. How many of you have that? I had Paul in my life, so many. What if he doesn't work? Come. Or what if he gets hit by a bus? Huh? Have you thought about that? So you want to build resiliency against Paul. And one of the very easy attacks is say, hey, Paul, today you don't come to work. Give me your laptop and don't do anything. And now let's test the system. And this actually is very, very devastating. So I always love to start with this kind of attack. But let's not do that right now. So chaos engineering is really a discipline to build an intuition, okay? But we don't just go around at breaking system in production like this, right? There's a whole path. There's a whole journey into, okay, I start chaos engineering now. How long does it take for me to actually break things in production? It can take weeks. It can take months and years, right? It's a journey of trying to build resiliency. And that's all what is chaos engineering is. We want to avoid the I think the system will recover. We want to have, I know the system will recover, okay? And chaos engineering is the whole method around trying to prove an assumption, okay, that I know the system will recover. Okay, so how many of you had outage that happened in the nights, on Christmas, on birthdays? Two of the biggest outages in my life were Christmas. The third one was my birthday. And that was quite normal that all the other outage was Friday evening, Saturday, Sunday. You know, Friday is when everyone wants to go home. It actually also when things tend to go wrong. I don't know what is this law. It's probably the law of no one is at the office, stuff is going to break. But actually, that's exactly what happened. And chaos engineering wants to break things when everyone is in the office, okay? So that you have all the best engineers at work ready to jump in and try to fix things versus having one guy on Friday night wanting to go out, pretty much already having had a couple of beers, not ready to take the system down. And this is exactly what chaos engineering is, okay? So when we do chaos engineering experiment, usually it's at 10 in the morning. Actually, if you start your chaos experiment or breaking things in the morning, people are not ready. If you go too late, people want to go home. So 10 a.m. is the good window to do that. And especially you want to avoid doing it at 1 a.m. in production when your boss is calling. You know, when I had outages, the first thing that happened is boss calling. And it was 1 a.m. I was already all stressed trying to fix the system. The boss calling is things are done. I know, you know, and we don't want that, right? It's escalating, it's very sweaty, you start to lose all your mind, you become really stupid, you know, that's what it is. So chaos engineering is really, we try to avoid this situation where we are stupid, okay? And usually when you present chaos engineering to your boss and say, all right, I went to talk on chaos engineering, Adrian said we should break a database, that's how it looks like. So don't go Monday morning and tell to your boss, hey, I had Adrian from AWS say we should break the database. That's not what I'm saying, okay? Twitch, don't break stuff. What I'm saying is actually a very good thing to start doing. And something that is very important, and Nora Jones from Netflix said that very beautifully, is that chaos engineering doesn't create problems, right? It actually reveals them, which is great. And it reveals them when all your neurons are active. Okay, so I often get the question, who is actually doing chaos engineering? Because I showed the microservices of Amazon, Netflix, Twitter, but actually chaos engineering is practiced by a lot of different organizations, from very small to very large. This is a map maintained online, if you want to see, of all the work that is being done. It's not me maintaining the map, actually, it's a very cool guy that is doing this work, but it's a very interesting way to see who is doing what. So if you're interested into chaos engineering, really have a look at here. And you see this company from Facebook, Google, Dropbox, up to Netflix, Yahoo, pretty much all the company have some sort of chaos engineering. And I'm not talking chaos, because that would be everyone. OK, so what is really chaos engineering? How do we do it? Because that's the important thing. Chaos engineering, you can divide this into a few phases. And it's phases that start from what we call a steady state, and it go up into trying to make an hypothesis, verifying the hypothesis, and then eventually fixing the stuff. So what is steady state? Let's start with that. Steady state is the idea to have a metric that shows you the normal operation of your system, right? What is normal operation? That's a good question. So a normal operation is a curve that shows how your system behaves during the day, during the night, through chains of traffic. And this is kind of a normal patterns that you have in some system. You know, this is week 1 and week 2 on top of each other. And you can see kind of the system behaves kind of consistently. So the 2 weeks are kind of normal. There's no big problem here. And this is exactly what a steady state is. Now, steady state shouldn't be CPU, shouldn't be memory, shouldn't be stuff like this, because at large scale, you can have a jump in CPU, but actually the user experience is still good, right? So it doesn't mean you should raise the alarm and wake up everybody and say, OK, let's fix stuff. Steady state is actually a metric that should be related to your business need. And one of the best steady states that I know of is the one from Netflix. Netflix has a steady state called the pulse of Netflix. And the pulse of Netflix is very interesting. It's how many times people click the play button around the world. It's quite funny. How many times people click a play button. You know why they do this? It's because if the video doesn't load, people tend to click several times. And if it doesn't load, it means there's a problem. And since you click several times, you're pissed as a user, right? So it's a direct view of customer experience versus the system. And this is a beautiful way for Netflix to measure the steady state. And they can actually predict very well the steady state of Netflix across the days, the weeks, and the pattern is very, very normal. OK, so at Amazon, we also have a couple of steady states. If you heard me yesterday talk about the multi-region systems and latency, we did some experiments at Amazon, and increasing 100 milliseconds latency in the UI, in the Amazon.com retail site, had an effect of 1% drop in the sales. Right? At the scale of Amazon, 1% sales drop is pretty big, right? So that's a direct metric of our business, right? Because our business is selling goods on the platform, right? So we have a metric, 100 milliseconds, increase of latency, create some sales of drop. So for us, measuring sales on our system is it's a good metric. So if we see dramatic change in sales patterns, we know that the system is experiencing issue. Maybe it's an issue in checkouts, so then it's a direct customer experience, or it's an issue in some of the recommendation service that don't work. It's also a customer experience that is degraded. Google, they did similar kind of stuff. So Google, 500 milliseconds latency, reduced the search by 20%. When your search is the business model, it's quite dramatic, right? And Yahoo did something similar. So these are kind of interesting steady states, right? So the number of search, the sales, and then the number of time a user clicked on play. So when you work at defining the steady states, don't just go the easy way towards application metrics or network metrics, because it's not only this. It has to be a combination of a user and the system interaction, OK? So once you figure it out what your steady state is, and you're able to monitor that steady state, you go into an hypothesis. And the hypothesis is exactly what I said before, is what happened if I switch off my database. When you do that, you have to get everyone in the room and ask yourself the question, right? But don't let everyone in the room answer to each other. Actually, ask everyone in the room to write down on the paper what they think is going to happen if the database goes down. And you should not just have software engineers. You should have database engineers. You should have network engineers, the UI designers, project manager. You should have everyone that is involved in building the application, okay? And you know why? It's because if you ask anyone in the company what happens when you break the database, everyone is going to give you a different answer. Actually, the first time you're going to do that exercise, you can stop here and say, oh, why do we have different answer? Why no one knows exactly what's going to happen? And this is actually a very good revelation that there's a problem. Because everyone should answer the same thing. Because we should work towards the same goals, right? When you build system. And if you don't build this in your documentation, how an engineer is going to build the system to know, OK, if my database goes down, then I should have a degradation of service. How many of you have database in your applications? Right. How many of you have a master database? Right. How many of you have read-only in your application? Read-only. So if my masters goes down, if I break my database, I can still have reads to the reads replica. How many? 1, 2, OK, 3, 4, few. And that's exactly what the point is. Imagine you're Netflix. Imagine your business is to serve video, and your database goes down. Should that affect customers? Your business is delivering video, it's not storing data in a database, right? So if your database is experiencing issue, you should be able to degrade yourself into a read-only mode, right? Because that's your business is actually trying to move away the failures that don't impact delivery of your video, right? Imagine if you have an authentication system that fails, and your users have paid to play videos, right? Do you just tell them, oh, sorry, authentication doesn't work? You can't see the videos you paid for. What should you do? Should you fail, or should you fail open? Fail open means if my authentication system fails, I let every user to look at every video, because that's the best user experience, right? That's what they paid for. It's not their problem that you have had problems with your authentication system. So these ideas like this are very important to talk about. And when you have everyone talking about an hypothesis, everyone should have exactly the same answer. So the first thing to fix is, why do we have different answers? Now, let's make an hypothesis that eventually, after a few exercises, you all give the same answer. Never, ever have one person say, I think, and then let it go. If you hear one person say, I think the system will recover like that, that should be a big, big interrogation mark, okay? Because I think just gives you the idea that I'm not so confident. And when you want to do chaos experiment, you should be very, very confident. Let me give you an example. I was a few months ago with a company in Iceland. It's a big company dealing with a lot of user data. And I simply asked them the question of, is your AWS account MFA protected? MFA means simply that you receive a text message, or that you have to put a second number to verify that you're that you are the right account owner, and it's really a security best practice, right? And everyone in the room said, yeah. But there's one guy on the side, this shy guy, that said, I think. And I was like, what do you mean you think? It's like, is it protected or not? And we went to verify, and guess what? The account was not protected. So you had 15 people in the room plus one saying, yes, it is, and one that says, I think. And actually, the account was not protected. They just had a small reorg, had to open the account to transfer to someone else, and had forgotten to re-enable MFA. So the idea of the problem with that is humans, right? Humans, we tend to think that a system was like this 2 weeks ago, therefore it's going to be like this now. If you don't verify, you're in big trouble, okay? So I have systems that verify all the time. So if you have anyone that says, I think, stop there and go verify. Don't break stuff that anyone says, I think it should recover. go and do chaos experiment and break things when everyone believes the system will be resilient. And that's the whole idea. You want to break things to verify an hypothesis that something is resilient. And this is chaos engineering. Now, that's exactly what I said. So don't break things that you know is going to break, right? Now, once you have done your hypothesis and say, OK, what is happening if I break my database, and everyone agrees, OK, the system should go in the read-only mode, then you can design an experiment and say, OK, how am I going to prove this in production? Or should I go and break the whole production system? Or should I design a small experiment within the production environment to isolate people and see what happens there? And this is exactly what designing the experiment is figuring out the scope of your experiment, figuring out which users are going to be affected, what are you going to do. Never, ever, ever, ever start with 100% of the users in production, right? It makes sense, right? So always start with a small set of your users and slowly increase the number of users and closely go to the production system. You can, of course, start with testing staging systems and then build confidence in your architectures or your software system and eventually go to production, right? But the end goal is really that you will run eventually an experiment in production, okay? You don't have to start in production, but the end goal is like this. So you pick your hypothesis, you define the scope, you control the blast radius, and then you need to figure out the metrics. Okay, so metrics is being able to know, detect when the system goes down, notify, all these kind of very important metrics that you will have to measure, because when you make an experiment, it's a scientific experiment, you want to use data. You don't want to just say, OK, let's break, and then check what happened. You want to have measured data so that you can go back to the experiment and say, this is exactly what happened, this is a timeline, and then understand exactly what happened. So picking up the metric is super important. Once you do that, make sure that you have a return button, and that's the button that you can stop an experiment. Very often at the beginning, you will notice that some experiments might go wrong, that your assumptions are not what you thought they were. So I'm breaking my database. I thought the system was recovering, and you noticed after 30 seconds, OK, the system is still not recovering. Let's stop the experiment, and then you should be able to come back. So when you destroy a database, it doesn't mean you actually should physically destroy the database. You must say, I'll remove the connection, and then I'll put it back, right? So be smart when you say, let's break the database. Make sure that you can actually put it back right away. In the same in the cloud, if you go and say, OK, let's break or let's remove the database, don't just say, oh, go on my instance, on my database, click delete. No, all right? Just remove or add a security group, remove the connection, do a change in the network. With one click, you are able to come back, right? So be careful what you're doing. So you have your back button, you have your emergency stop, and now you're running your experiment. The best way I've found to do experiment is through Canary deployment. And I love, especially for large-scale systems, I love to do experiment on the DNS level. And this is just one way of doing it. You don't have to do it like this. But Canary deployment for me is good, because Canary deployment means I have my normal version, so I have the normal system in production, and then I create a second environment, and I only push maybe 1% of the traffic there, right? Or 0.1 if you have millions of users, right? And you can also figure out which user you push first to test the system. Doing that, you can very, very fast, through DNS failovers, push back all the traffic there. And when you do a Canary deployment, just don't say, OK, I'm going to start with 1%, 2%, 5% of the users and say, oh, it works. Let's move everything. Go all the way. 1, 2, 3, 4, 5, 6, until 100%. And wait. Systems, like with a lot of cache, need warm up, right? So when you move the number of users, Be patient. Don't say, OK, 1 minute, system works. I'll increase 10%. Oh, it works. Because the system most likely will go down. I've seen system break down after 90% of the traffic was tested after an hour of traffic, right? That's what it is. When you have large-scale systems with a lot of cache, with a lot of messaging queues, the system takes time to warm up, OK? The beautiful way with that is you can really flip back. So this is why I like. And you don't have to do a DNS level Canary. You can do on the function level in Lambda. You can do on the container level with a load balancer, or on EC2 with a load balancer. It really is up to you to do that. Once you do that, you have the metrics. You're starting your experiments. You've broke the database. You have all the metrics. You stop the experiment. Then you need to verify. And verifying is you look at everything that was written in the hypothesis phase, and you go one by one. Is it exactly what we thought that was going to happen? Is the reality representing what people think, right? And this is where you have very interesting conflicts. Maybe the time that you waited for the system to fail over was not what you thought it was. You know, for example, when you do a Canary deployment or a DNS failover, there are TTLs, right, in the DNS. Right? Is it 30 seconds? Is it 60 seconds? Is it 3 minutes? So all this time that the system does the change needs to be measured and verified. And this is very important, right? Quantifying the results. And for me, the most important, time to detect. So one of the big outages that I was talking about was a failure in our detection system. Right? Our detection system failed. So that means we never realized, or we never got notified that actually the system was having a failure. So we had first the minor failures. We had the cache system going down. The system was supposed to recover, but our notification system didn't work. Actually, we didn't get paged. So we were all waiting, and nothing happened, right? And that's a big problem. You know what the problem was is the escalation path. One person had left the company, and the escalation path had not been updated. It sounds stupid like this, but actually that's always what happened. Actually, big outage is not just one thing. It's a collection of small things that all happen at the same time and create catastrophic failures. And this is what it is. And if we would have been paged, there wouldn't have been a problem, because we would have been paged, maybe been paged after 1 minute, and then we would have been able to fix the cache. But it took 27 minutes for us to be notified. Actually, it's the users that told us, the system is down. It's like, what? We didn't, oh, wow. And in 27 minutes, the system degraded a lot more. We started to have cascading failures. We're starting to have a lot more requests on the database. We started to have update requests that was blocking the tables. And then all of a sudden, the whole system went into cascading failures, a catastrophic one, right? So it's just like a few small problems put together that really creates problem. So the first very time to detect, super important. And of course, you need to have a quantification for everything that your company wants. And time to clear all is super important, or time to inform the public, all this kind of stuff. OK, so one of the most important things when you do quantifications of results is do not blame people. Actually, I've seen cultures being broken down because of blaming. So for example, I'll give you an example. 8, 9 years ago, I cleaned a database in production. Actually, I destroyed the database by mistake. I thought it was a testing environment. I deleted it. I like to say I cleaned it. I deleted the database, and when we did the debrief, no one blamed me, right? And actually, I think I wouldn't be here, to be honest, if anyone would have blamed me, because I already felt so bad. Yeah, as an engineer, you don't want to do stuff like that, right? Because that makes you feel pretty stupid. I was hired, and that was my 3rd week. Yeah, it will happen to you one day, right? And actually, my manager was really nice that he didn't blame me. Right? So that's super important, right? And if you would have said, oh, you're stupid, you can't do this, and then I would say, okay, I'm going to go and make steaks and hamburgers because that's what I'm also good at, you know? I was just learning, you know? And you can make mistakes. So instead of blaming me, he said, okay, that's done. What can you do to never do that again? And then we started to build tools, right? Resiliency tools. And then we started to build a lot of automation tools to avoid this kind of stuff. And actually, this is how I got interested into breaking things. OK. So don't blame anyone, because actually, that will destroy your company and your culture. And then when you do that, when you do the verification and you want to go through the whole thing, you need to have some kind of methodology to understand what really happened. You know, at Amazon, we like to use a methodology called the 5 whys. It's a methodology that just starts with an outage, and then we ask, why did we have an outage? Because our database went down. Why did our database went down? Because Adrian deleted the database. Why did Adrian delete the database? Because we didn't have, because Adrian was using the production environment without thinking he was in production environment. How is that possible? He said because he had 2 terminals with the same color, same font, and he thought it was that. So we started to build tools, you know, to really understand what was happening. And what was happening is that there was nothing for me to know, obviously, that I was in a production environment. And this is why we started to build tools to make sure that when you log in a system with your terminal in production, it's red, right? And when you click delete, there's verification 5 times that, are you sure you want to delete that? Are you really sure? Add an MFA, just to make sure. Right? And this is what you should do. Right? So now the 5 whys methodology is being criticized quite often, because if you ask 10 people in a team of why a system went down, actually you will end up with 5 different versions of the why. But at least it gives you an idea of, you know, where to look at. But don't stop here. Ask yourself a lot more questions like, why didn't anyone help or advise or try to help? Right? That's, again, related to blaming. In teams, someone might say, the database went down and Adrian was left alone trying to recover everything. Why no one helped? You know, all this kind of stuff. And this is very important. Go deeper into the problems. Try to figure out. Ask more questions. And this is super important. And few things to always remember when you try to find the root cause. Even though there's never one root cause, there might be several root causes, because, again, like I said, failures are not one thing. It's a collection of small things happening at the same time that create monstrous, catastrophic failures. Okay? What might seem benign, if it's happening at the same time as another, so if a cache goes down at the same time as your alert system goes down, that's bad. If any of those would have gone down isolated, no problem. Okay? So always remember that things are not isolated. And then you have to fix. And here I really have no idea. Don't know what to tell you, but because it's really depending on your application. When you have a problem and you have identified, you should make a correction of error. But don't wait to implement the changes. Okay, once you've understood what is wrong, don't say, oh, but our customers really need more features, so let's wait a little bit to implement the fixes. Okay? Couple of months ago, I was working with a company. They made a beautiful chaos experiment, a beautiful analysis of the root cause. They had a very beautiful corrections of errors, but they didn't have the time, or the management said, we don't have the time to do the change now. Let's wait. A week later, same stuff, much bigger. Right? So what turned into a 20-minute outage in a chaos experiment that could be recovered and well understood, ended up in 27 hours down. The same thing. Simply because they didn't take the time to implement what they had what they knew had to be implemented. At Amazon, when we do corrections of errors, the service teams that writes those corrections of errors, the principal engineers, can delay anything in the roadmap. Actually, the corrections for the problems have high priority over anything else, okay? And this is super important. So the next slides are more a collections of some of the big patterns that you need to have implemented in your architecture. This is some of the stuff that actually broke all the time. That if I had outages, this is what happened. So this is just a collection of some of the top patterns that I've seen and that you should probably think of if you want to be resilient. One of the first is, of course, understanding that. And if you were in my presentation yesterday, it's simply understanding that if you put two parts in parallel, actually the availability of the system increased dramatically. So for example, if I have a part X and it's 99% available, isolated, it means this can be down 3 days. But if you put this in parallel with the same system, it's 52-minute downtime, right? So the availability of the system increased dramatically to 4 nines of availability, which is very, very good. If you do the same thing another time, so a third part, you increase your availability to 6 nines, okay? And this is probably the most important patterns to know, is like putting things in parallel in the systems increase the availability of the system dramatically. And this is also why we always say you should architect your application across multiple AZs. In Amazon, we talk about regions, and in regions, there are availability zones. Each availability zone has 1 to several data centers. And when you architect an application, you should always be across several AZs, right? So that if an AZ is experiencing issues, your application is available in other AZs. When you do this, you need to make sure that your application is stateless. So that means that your application can take requests, or that the same service in one AZ or the other can take 2 subsequent requests without any problem, right? So that means service A and B need to share all their states with services in other AZs. And this is what we call stateless. You never store state locally on your function, on your container, on your instance. Always share that state with other through a cache, right? So Redis, Memcache, RabbitMQ, if you want to do that, Elasticsearch, DynamoDB. There's a lot of different solutions. I tend to prefer Memcache and Redis. When you do that, you can make your system pretty much resilient, because if my AZs go down, my state is preserved, and then the service can recover. And those services are, by default, orchestrated across several AZs, so the state will be preserved, okay? Another pattern which is super important is auto-scaling, right? Auto-scaling is the idea that with traffic, you change the pattern of your application, or that you increase resources. But actually, the interesting thing for resiliency is when you use auto-scaling, it's also a self-healing system, right? When you use on AWS auto-scaling groups, you put always a minimum, right? A minimum of 1, for example, or 2. And if any of the instance experiences issue, the system will just shut them down and restart 2 more instances automatically. And this is the basic version of self-healing. And this is very interesting patterns for making application resilient, right? Because then you don't have to go and log into the system and say, oh, I need to start another instance. The system does that automatically. Another interesting pattern, of course, I talked about auto-scaling, is decoupling, okay? We are talking about microservices all the time. What is very important is having A being able to talk through B without knowing B exists, right? So that actually the system are totally decoupled. And there's few ways to do that. My favorite one is to use queues, right? So instead of having system talk to one another, you use a queue, so that if B is experiencing issues, A can still operate normally and send data into the queue, right? Of course, you have to make the queue resilient, right? But it's much easier to do like that. When you do like this, the most common pattern to use in decoupled system is to isolate your API instances or your API customer-facing API with worker instances, okay? So what happens is, imagine I'm a user and I'm at a request, like I say, my API do something. Instead of trying to do the something and then return, I take the ID and I return immediately, right? And this is the idea of having asynchronous API. So you take a job, you put the job into a queue. Once you do that, your worker can get the job from the queue, process that job, store the information in the cache. That does two things, right? It allows you to scale this independently of that, because APIs are very often CPU bound, or maybe I/O bound, depending on what system you're using, and this might have totally different characteristics, right? And the very interesting thing with this one is you can start decoupling things even more, because now I have my data stored in cache. What you can do is push notification to the user, and then the user can come and fetch the result. One of the most important things with this is actually that you don't necessarily only have one queue. Because when system experience failures, you don't want to not let the system work. You want to degrade it. And this is a very beautiful way to degrade an API. For example, you might, in a system, you always have critical API and non-critical API, right? Critical API, you want to prioritize that. So if, for example, you have some failures happening in your system, you might say, I'm only going to take critical API and deprioritize all the stuff that I don't care, right? And this is a very good way to do it. Queues per priorities. Another thing what you can do is on the database level, right? One thing that very often happens is people use database, and that database takes the reads and the write. One of the first thing to do is actually split. I have a master database and then some read replicas so that you can have reads and writes happening at different places. Very often, the database, when they write, they lock the table, right? So that means you can't read as much as you want. If you do that, you can decouple the writes to the reads and actually scale your application. So that means it's a very easy way to scale. If you use Amazon RDS, you can have 5 read replicas, right? If you use Aurora, you can have 15 of them. So that means there's a lot of way to scale your reads. And it's also a very good way to do read-only mode. The questions I asked was, if my master database goes down, well, my read replica are going to work. And you can very, very easily have an application that is read-only. Right? And then you might want to store transaction or store things here in a queue and then push them a bit later to the database once it's recovered. So it actually gives you a very easy way to do graceful degradation, okay? So from master failures to read-only mode. And many, many companies use that. And you don't necessarily see it because your application still works. Another pattern is, of course, database federation. Very often when you look at databases, there are tables that are absolutely not related. So one easy way to scale the database is actually to remove the one from another, right? Put tables in different databases. If they don't have a relation to them, you don't do joins between all of those, it doesn't make sense to have them. At Amazon in 2007-8, we did an analysis of all the database query that was happening in our system, and 70% of them were not transactional, right? So we were using a lot of transactional database, but 70% of them were not transactional. So what we did is we actually had a federation and moved the transactional database to a smaller cluster of transactional database, and then implemented DynamoDB, right? And this is why we now have DynamoDB. So you can also do federation of different type of database. You can have NoSQL and SQL. You don't have to make one choice. And you know, the SQL versus NoSQL war is just for internet memes, right? You have to use both, right? They have qualities that are actually important. And the last resort to scaling your database is, of course, sharding the database. That's on the shard ID. It's maybe more advanced. I'll leave it in the slides. I want to move on because I'm running out of time and I have stuff I want to talk about. Important thing is do not store transient state in database. Actually, some of the biggest outage I've had was because of updates query on the database, right? When you do an update query on the database, it means you want to update a value in the database. That means you mutate that value. So why did you put it in the first place there, right? There's no reason. So a database should only be used for data that is not mutated. If you want to mutate your data, use systems like Redis or Memcache or a system that actually alleviate the request to the database. If you want to query a database, make sure it's a query that is very important for the database. No, don't mutate it. Right? Only do reads and write. If you have to do updates, think why you do that, okay? And most of the time, it's because you want to mutate data, and that's bad. Use cache or use other system to do that. A very important thing, what happens in large-scale systems is cascading failures. So you saw we had 2 availability zones and the load balancer pushing traffic from one AZ to another. The load balancer is the mom, right? The babies are the availability zone. One baby is experiencing an outage, it falls. The mom switches all her attention to one baby, and then the baby falls, right? And this is exactly what cascading failure is. The problem here is that you have resource utilization, right? If you have 2 AZs and you have a load balancer distributing traffic between 2 services and they have 70% resource utilization, and you flip all the traffic from one to another, all of a sudden you have 70% plus 70%, and that's a cascading failure. So when you design systems like this, always make sure that when you flip, you don't create this kind of cascading failure mode, okay? Another important thing, I want to make a test. How many of you are Python developers? Cool. How many of you know the default timeout for the request library in Python? What? No one? When you design system, you don't check timeouts? All right, let me tell you a story. It's a quick story. I'm running out of time, but imagine I have a user and I'm making requests to a database, right? Very often, I make a request. I'm a 1 user, so this is 4 users, and I make a lot of requests. Imagine my number of requests increase and my database starts to slow down. What happened? Well, you have to look at the system, man, and then you have to say, well, imagine, oh, sorry. I'll go back, the system is just crazy. Hello. So I'm making my requests. I create an insert. My database is slowing down. What if actually the database slowed down so much that the timeout here fails? So imagine I didn't implement a timeout, right? But now imagine actually the client side, which often have default timeouts of, let's say, 5 or 10. After 5 seconds or 10 seconds, decides that, OK, I'm going to stop the request. Well, you have one request that is blocked to insert data in a database because there's no timeout. This is timing out, so my user makes another request. OK. My request tries to make another insert into the database. My database still doesn't accept the insert. There is no timeout. My connection still locks. My user does another retry because he couldn't insert. It never gets. And all of a sudden, you get something like this. Have you seen that error? The error is that your connection pool is out. And this is exactly what cascading failure is, right? Because now, your user cannot make API requests anymore. It gets 500 or 400, depending on what you do, right? And this is super important. So timeouts not implemented can kill your system, right? And this is also some of the outage I've seen is because outage by default are actually very often infinite. And you don't believe me? This is the Python documentation for the request API. You see here? By default, requests do not time out. And Python developers, trust me, you want that to time out. Right? And actually, many of the libraries do not time out. Okay, so when you implement the system, make sure you do. If you want a timeout, there's some decorators in the Python. This is for Python developer. I'll leave it in the slide so you can do this. So really, make sure you have those timeouts. Then you could have done a lot of other stuff. You could have waited instead of retrying immediately. And this is called exponential backoff. You probably heard about that. So that if I retry, every time I do in a retry, instead of doing the retry immediately, I wait, for example, 2 seconds, then 4 seconds, then 8, 16. So I exponentially, my wait time, my retry time, my wait before I retry actually increases. And this is called exponential backoff. And exponential backoff, you also want a jitter, and there's been some research paper that shows that exponential backoff without jitter can also create problems. So do make sure that your library have exponential backoff. And actually, very often they don't, okay? So make sure when you connect to systems, they have exponential backoff. You'll all have the slides. I'm running out of time. I'm being told I need to stop. So thank you very much. Have a good afternoon.